So this work was done in collaboration with Mikaël and Viktor Kuncak. Let me first tell you what we mean by synthesis here. Synthesis, it's a process of creating a program without programming, but by giving a specification which relates the inputs and the outputs. So it could be a formula which describes your program. And the goal is to generate the program automatically from there. So the benefits from synthesis are the fact that it enables users which don't have programming experience to create programs. And also it ensures that the generated programs will satisfy the specification that was given. In this talk, the specification is going to be a set of input-output examples. And the nice thing about input-output examples is that they can be easier to read than the program, so they can provide a good documentation for the program, a better documentation sometimes than the program itself. So the programs that we want to synthesize here are tree-to-string functions. The tree and strings can be used to represent many things. And I put some use cases here, like pretty printing objects that you get when you program, or printing XML-like structures to files, or serialization of any object to an XML or JSON string. So now we won't be able to synthesize any kind of tree-to-string function, but we look at a particular class. It has a fancy name, Sequential Single-State Transducer. The real name is even longer. But so these transducers, they operate on some trees, and the input domain will look like something like this. And this is an example of trees describing terms of the lambda calculus. So in the lambda calculus, you have three kinds of terms. You have variables, and then you have lambda definitions with a variable and a body, and then you have application of one term to another. And here is an example of a function which operates on this tree to produce a string. So it will traverse the tree top-down. Here for a variable, it just outputs the name of the variable. Then for the lambda, it uses these characters, the lambda characters, and it outputs the variable. Then it puts a dot, and then it recurses on the body, and then it encloses everything with parentheses. And the application is similar. You just separate the two terms by a space, and you enclose everything by parentheses. So sequential here means that we only look at functions which recurse on the children in order, and only once. So you cannot reorder children when you call yourself recursively. And single state means that you don't have the right to carry a state while you are recursing down the tree. So you have no memory of what you have seen before. But we will see that even this class has many challenges. So here it's the same function as before, and just to give you an example, for instance, on this lambda term, it will produce this string, and on this application of this lambda term to another variable, it will produce this string. Here is a slightly different function which puts the parentheses, for the lambda it's the same, but for the application it puts the parentheses around the arguments instead of around everything. So for the application it will produce a slightly different term. So the first problem that we look at is generating these functions from input-output examples. And you can see that the only unknowns from these functions are the constants that you put in here. So these are strings, and these are the unknowns that we want to find. We want to find these strings so that we are consistent with the examples given by the user. And the contributions that we have for this problem is finding the exact time complexity that it takes to solve the problem. And we do this by reduction to and from word equations. Well, I will give more details later about this, because we have several contexts in which we analyze the complexity. And well, however, there is a big limitation with the presentation of this problem, is that it's possible that the function that we generate is not what the user had in mind. If the user doesn't give enough examples, then it's possible that what we give will be consistent with the example that the user gave, but not consistent with other examples that the user had in mind. So that's why we look at the problem from another point of view. It's a problem of generating ourselves the question the questions for the user. So we will ask him, how do you output this? How do you want to output this? And we will only start from the tree definitions, and the goal will be to ask enough questions to be sure that we generate what the user has in mind, or something equivalent. And this is very challenging because in one way you don't want to ask too few questions, and on the other hand you don't want to ask too many questions to not bother the user. And so here for the contributions, we prove that you need, in fact, n to the power of 3 questions, and this is optimal, where n is the size of the tree definitions that I showed on the previous slide. And here we improved a bound n to the power 6, which existed in another context, but which also applied to this domain. And the main result of the paper is that, in fact, we can improve to a linear number of questions if we allow the synthesizer to analyze the previous answers from the user. So the synthesizer now can ask questions and can analyze the answers to decide what is the next question that it is going to ask to the user. So the outline, I will start by talking about the synthesis from examples and the complexity, and then I will talk about this second problem of generating the questions ourselves. So first, let me show you how the problem of synthesizing from examples is closely related to solving word equations. So, here we have 3 examples that the user gives, and the goal is to find the unknowns here so that the generated function matches these examples. And so let's give a name to the unknowns. So we have these unknowns now are string variables, and the goal is to find what they are so that we obtain what we want on the bottom. And in fact, each input-output example gives you a word equation on this variable. So the first equation, the first input-output examples gives you this equation, and in fact, it tells you that W1 and W2 must be empty. It's the only way that this word equation can be satisfied, where the dot corresponds to a concatenation of words, of strings. The second input-output examples gives you constraints about W3, W4, and W5. And here also this equation is easy to solve because there are only 2 x's in this string, so there is only one way to cut this string into W3, W4, W5. Then the last examples gives you this equation, and here also it's easy to solve. So in general, it's not so easy to solve because you can have many cut points in the string, and in fact, you can have exponentially many. So we prove that this is the function that you obtain in the end, which is the one we had before. In fact, we prove that the problem of finding such constants is an NP-complete problem, meaning there is no known polynomial time algorithm to do it. And I will give you a quick intuition on the proof. So we reduce from a variant of the satisfiability problem, Boolean satisfiability, which is called 1 in 3 sat. In 1 in 3 sat, you have Boolean clauses of the form 1 in 3 x, y, z, and you want to find an assignment to the variables so that exactly one variable in each clause evaluates to true, while the other 2 evaluates to false. So from such a formula, from such clauses, we generate examples, input-output examples that look like this. So you can see x, y, z as being a linear tree, and we say that we want the output of this tree to be just the letter A. What this gives you as a constraint is that exactly one of the constants corresponding to x, y, z should be A, while the other 2 should be empty. And in fact, it's finding such a function f, which satisfies this constraint, is exactly equivalent to finding a Boolean assignments where exactly one variable evaluates to true in each clause. But this is not the end. In fact, if the examples that the user gives are of a particular form, if they are closed under subtree, meaning that if every subtree of the input-output examples is also part of the examples, then this problem can be solved in polynomial time. And this is a very reasonable assumption because you could, if the user can give you an input-output example for some tree, he can also give you an input-output example for the subtrees of this tree. And well, here the proof, we also reduce to word equations. And we notice that the word equations that are generated by such classes, by such inputs, are of a particular form, and we call them sequential word equations. And we can prove that these sequential word equations can be solved in polynomial time instead of NP for the previous word equation. So in general, the word equations that you obtain when your input domain is closed under subtree looks like this. So you always have the variables which are on the same order, and that's why we call them sequential. And then on the right-hand side, you always have strings, which corresponds to the output that the user wants. And to solve this equation, we have the following algorithm. So first, we look at the first equation. Here you see that there are many, well, there are only two ways, I guess, in this case, but there are several ways to obtain W, W prime, and W second when you solve this equation. So we make an automaton which represents all the solutions of the first equation. And in general, this automaton can recognize exponentially many strings, but it will recognize them in a compact manner. It will only be of polynomial size. Then we build A2 and A3, here's the typo, similarly for the equation 2 and equation 3. And then we do the intersection of all these automata, and by checking emptiness of this intersection, we will know whether there exists a satisfiable answer for these equations. And here the important point is that in general, when you take the intersection of n automata, you have an exponential blowup. But because of the form of this automata, the particular form that they have, we have proven that the intersection here doesn't blow up, and you can compute this intersection of multiple automata in polynomial time. So that's it for the first problem. Now let me tell you about the second one. And the question was, how many questions do we need to ask the user to be sure there is no ambiguity in the function we generate? And which questions do we ask? And for this, we use the notion of test set. So it's a notion that exists in another context, and we reuse it here. And a test set is, here in our context, it will be a set of trees, such that if you take any two pair of functions, if they have the same output on this test set, on this set, T, then they are completely equivalent for all inputs, for any tree. And the question now from tree definitions, how can we compute such a test set? So we have given a new construction that enables us to, from tree definitions, to build a test set of size n to the power of 3. And this is optimal. The previous best construction was, as I said, n to the power 6. It's a very old result. And we match the known lower bound from the same paper, which was proven to be n to the power of 3. So for the lambda calculus example, you would have, in fact, in this test set, 44 trees. So this will be a lot of questions to ask to the user. So let me just tell you how this would work. You would generate the test set from the tree definitions. Then you would ask the user, what are the outputs for all of these tree definitions, for all of these trees? Then you would solve the resulting equations, and we can solve them in polynomial time because the test set falls into this category of closed under subtree. And then you have the guarantee that the generated function is equivalent to what the user had in mind, because they are equivalent on the test set. So the limitation, of course, is that answering all of these questions is tedious. And here you see that, in fact, we have only somehow 2 communication steps. So we ask the user, what are the outputs for all of these? And the user answers for all of these trees. But we can do better if we use back and forth communication. So the intersection that I talked about of automata, instead of computing it once at the end, we will compute it on the fly. and we will maintain this automaton representing the set of all solutions along the way. And then for each tree of the test set, we will try to infer the output based on the information that we have so far, based on the automaton that we have. And if we cannot infer it, that's okay. We will ask the output to the user. And then we will add this new information that we have from the answer of the user to the automaton by doing an intersection. And this seems like a small optimization, but in fact we can prove that this interactive process will only ask at most a linear number of questions out of the n to the power of 3 that it is going to look at. So it will be able to infer the output for many of the trees from the test set. Okay. Now let me give you a very quick demo. So here I have 3 definitions for a table. You have a class which represents the row of a table. So in a row, either you have no cell, or you have one cell containing an integer, followed by the rest of the row. And then you have a table. A table is just either you have no row, or you have one row, followed by the rest of the table. So when we start our tool, it will generate the test set, and then it will explore each tree of the test set. So it will ask you, how do you want to print no cell at all? So I just want to print it as an empty string, no row at all, empty string. And then here it asks me, how do you want to print one cell containing 42? So I want to print it like this, for instance. And here it was able to determine the output for another tree, the cell only containing 19. And then it asks me another question. What should be the output for one row containing no cell? So I want each row to be on a separate line, so I will put a new line here, and then enter. Now it's not able to find the output for this, but it's able to find 2 distinct possibilities. So it asks me, how do you want to print one row containing one cell? So I want to print it like the option number 2, so I just put number 2. Then it asks, how do you want to print 2 consecutive cells? So it's not able to understand that the brackets are what constitute a cell, because it doesn't know there are many possibilities in how to solve the word equations. So here I will tell it that I want it to be displayed like option 2. And here, I think it's the final question. It asks us how we want to print one row containing no cell at all, and then one other row containing just the number 42. So this is option 1, because we have an empty row and then 42. And then it's able to generate the function that will work for any kind of input. So here we can see that in the test set, there are 21 trees, but it only asked us 7 questions. Then if I wrote a small tree here, a small table, and then I call this function on this tree, and we obtain what we expect, which is this table. Okay. Before concluding, I will give some remarks about the related work. So the first reference I already talked about. It's about the test set for context-free languages. The second reference is maybe what is most closely related to our work. They also study sequential tree toward transducer, but they are allowed to have states in their transducer. The limitation is that they only look at problem 1, how to find the function from examples, but not how to generate questions from scratch. The other references are about how to check equivalence between 2 transducers. And this is very related to our work, because what we want to give is something which is equivalent to what the user had in mind. To summarize, we have studied the first problem of finding a tree-to-string function from examples. And we have found that the problem is NP-complete in general, but it can be solved in polynomial time when you have the reasonable assumption that the examples that you are given are closed under subtree. And we have looked at the second problem of finding a tree to string function from scratch, where we had to generate the questions ourselves. And here we have found that the optimal bound was we had to know the output for a cubic number of trees, but this can be improved to a linear number of trees if we are allowed to interact with the user. For our future work, we would like to extend this to larger classes of tree-to-string function, and we think that the techniques which are developed there could be applied to these larger classes. Thank you for your attention.
Let's see. Okay, very cool, very nice. I have a question, which is, so when I write printers like this, I usually split them up into two separate functions. So just to stick with the example you have here with the row and the table,
yeah,
I would imagine that, like, if I was writing this, I would first have a printer for rows, and then I would have a printer for tables, right?
Yes.
So in general, is that easy to do in your framework, where if I want to write a kind of, I want to build up a printer in this kind of bottom-up style, would I essentially just say that, look, here's already the code for, let's just say, here's the code for rows. Maybe I do this interactive thing and I synthesize the code for rows. And then can I just say, now at this point you should call out into the printer for rows, but now solve out the other stuff that you need to do to print out tables, or does the whole thing have to be monolithic?
For now, it has to be done in just one iteration, but maybe doing something modular, as you suggest, would be better. In the end, maybe we could present just the function as two separate functions, because what we generate in the end is just one function, right? We would have one function which works on the types const row and no row, and one function which works on the other types. But what we cannot do is sometimes you could have mutually recursive functions, right? Which somehow each function maintains a different state. And this we cannot do at the moment. You need to have the two functions really separated.
Very nice work. So I have a question. So for example, sometimes when we want to print a tree, the printing condition depends on the child in the parent side. For example, if the child is empty, I want to print nothing. If it's not empty, I possibly want to add a parenthesis, something like that. How hard is it to add dependency between the parent and child? What might be the bottleneck for extending this?
The bottleneck for looking at the child?
Yeah, for adding constraint between like parent and child. So now currently it's content independent in your case, right?
Yes. For now, the content is only dependent on the current node.
Yeah. Just curious about like what's the possible bottleneck?
So the problem is that basically you would have a function which will do a deeper pattern matching maybe. And I think the functions that you would obtain will not be of the good form that we have. They will not be sequential word equations as we had for this case. But it's something that we want to think about and explore further.
Yeah, cool, thanks.
Thank you.